Assalamualaikum warahmatullahi wabarakatuh. My name is Muhamad Hanif Here I would like to present my final year project, which is experimental investigation on the effect of helicopter rotor half wake to the vertical tail. The content of this slide include introduction, experiment, result, discussion and conclusion. Nowadays, helicopter tail shake phenomenon is an issue of major concern for rotorcraft industry, and this tail shake phenomenon remains as a long-drag issue that adversely affected the overall performance, occupant comfort, and handling qualities of helicopter. This phenomenon affects helicopter lateral stability as the unsteady wake produced by the main rotor hub hitting the vertical stabilizer and induce tail vibration. There are many articles, papers, journals have been talking about this phenomenon. A paper of experimental research on helicopter tail shake phenomenon written in 2008 state that the wake occurs when the model is nose down at -5 degree, and as the main rotor hub rotational speed increase, the turbulent intensity due to the wake excitation also increase. Here is a picture of the test configuration where the value illustrated in this table here is representing a plane B for speed of 0 rpm and 900 rpm at point 1 and 2. Both points, the turbulent intensity shows the increasement in percentage as the speed is increased. Same goes for another paper of computational fluid dynamic studies on helicopter rotor hub assembly wake written in 2010. They said that the higher speed of rotation, the more turbulent intensity produced by the main rotor hub. This study also found that ellipsoid pylon can reduce turbulent intensity compared to the rectangular pylon. If the pylon becomes higher, the turbulent intensity becomes lower. In addition, the firing effect also can reduce drag caused by main rotor hub since the turbulent intensity is reduced as shown in this graph. In 2014, a study of CFD, simulation of the rotor head influence to the rotor fuselage interaction, found that there are pressure different due to the main rotor hub wake on the vertical stabilizer represented by the region of red dashed line here as shown in this figure. So this research will provide that the tail is vibrating due to the hub wake. From a thesis of unsteady aerodynamic weight characteristic of a generic helicopter, Amirul Arif stated that when no pylon implemented, there was a high wake fluctuation in the downstream. The implementation of ellipsoidal pylon greatly reduced the wake fluctuation. The main objective of this project is to quantify the frequency and horizontal displacement of vertical tail due to the unsteady helicopter rotor hub wake. The scope of study for this project covers literature study, prepare the wind tunnel model, execute the wind tunnel campaign, and for various helicopter advance ratio to quantify the frequency and horizontal displacement of vertical tail due to the unsteady helicopter rotor hub wake. The experiment was conducted using UTM LST. In order to quantify the frequency on the vertical tail, an accelerometer is installed in the vertical tail so that the frequency can be quantified. The sampling rate of frequency is 1000 Hz for 10 seconds. Here is the table of the test configuration for this project. The variables of the experiment are different at ratio, vertical stabilizer, and shape of pylon. Before running an experiment, it is compulsory to do pre-experiment first. The accelerometer is calibrated by recording an acceleration of gravitational in z-axis of the accelerometer. This calibration was repeated 3 times to make it more precise. The sensitivity obtained from the result is 0.3254 volt per gravitational, which means it is in the range of the sensitivity written in the datasheet as illustrated in this graph and a table here. As you can see, here is the picture of the experiment, how the model was installed in the test section. Here also include the schematic diagram, result and discussion. Here, I will be presenting about the wake region. static analysis, dynamic analysis, and also lateral displacement. From previous feasibility study, about 25 types of helicopter, the parameter of tailbone with vertical stabilizer is satisfying since the location of the vertical stabilizer is about 4R to 6R as mentioned by Arif in 2019 that it is the common area for vertical stabilizer and he found that the hub wake also occur in that region. Patrick in 2017 note that when the empennage are caught in the hub wake, the pitch and yaw stability are decreased and the stabilizer become less effective due to the pressure loss in the wake. So this study provides two types of vertical stabilizer as we can see from both of these graphs, the power acceleration amplitude are symmetrical about 0.6, which is higher than cambered airfoil about 0.1. The comparison can be seen at advanced ratio of 0.83 for both of the graphs. Since the cambered airfoil has lower power amplitude, it means that the cambered airfoil has lower vibration when it caught by the hub wake compared to the symmetrical airfoil. Knowing that in the x-axis here is the omega. One omega is representing one complete rotational rotor blade. Next, a paper written by Ishaq in 2010 states that the increment of rotor RPM for the same wind speed will increase the aerodynamic force. Same goes to the same rotor RPM with the increment of the wind speed, the aerodynamic force will be increased. The study was focusing on the drag force which related to the hub wake. It means that the hub wake is increasing due to the increasement of main rotor rotational speed and also the increasement of the wind speed. This study also found the same thing where the power acceleration amplitude is increasing corresponding to the increasement of the wind speed when the rotational speed is remain statically at 0 rpm. So this may suggest that the vibration occur at the vertical stabilizer is coming from the hub wake only. For both figure here, clearly show the highest power amplitude is at 30 meter per second, then followed by 20 meter per second, and the lowest power amplitude is at 20 meter per second. In 2018, note that the source of vibration produced on the vertical tail are from the blade faces, frequency, and wake that hitting the vertical stabilizer. So, in order to study the vibration from the mechanical system, the forward speed is remain as 0 with various rotor rotational speed. From the graph, the power acceleration is decreasing when the rotor rotational speed is increased. But again, the power acceleration amplitude of symmetrical airfoil is lower than cambered airfoil. Note that this acceleration are not come from the hub wake. It just come from mechanical system of rotor rotational which has been transferred to the tail boom. Vertical stabilizer is used to improve helicopter stability. Vertical stabilizer can be less effective when it is caught by the hub wake during the forward flight as mentioned earlier. In this journal, which is written by Rich in 2016, he mentioned that this firing may reduce the wake if excited by the main rotor hub, which indicate the lower turbulent intensity around the vertical stabilizer. Since the turbulent intensity around the vertical stabilizer is reduced, the vibration on the vertical tail also reduced. In their study, they found that the elliptical firing is the best generally applicable hub firing. In this study, there are two types of pylon used to reduce the wake, which is ellipsoidal pylon and rectangular pylon. The power acceleration amplitude is decreasing when the pylon is implemented as shown in both graphs here. Both of these pylon give reduction in acceleration for both vertical stabilizer as shown in this graph. This may suggest that ellipsoidal pylon reduce the wake better than rectangular pylon. So that means the pylon firing is reducing the wake so that the vibration also reduce. From previous discussion, These are the pictures that explain how the vibration behavior corresponding to the different configuration. First, NACA 0021 shows higher fluctuation displacement compared to NACA 4415. That means NACA 0021 experience more vibration compared to NACA 4415. Second, when the forward speed increase, the vibration also increase with higher fluctuation amplitude. It shows that the wake is increased when the forward speed is increased. Third, at advanced ratio of 0.55 with 1600 rpm and 20 meter per second without fairing the vibration showing the highest amplitude of displacement. By installing the pylon fairing, the wake will be reduced. So both of these pylon configuration reducing the vibration on vertical tail. Fourth, for more comparable at advanced ratio of 0.52 where 1600 rpm and 25 meter per second, amplitude of displacement for ellipsoidal pylon lower than rectangular pylon. That means ellipsoidal pylon reduce more vibration compared to rectangular pylon. Summary for this analysis. First, wake region occur at vertical stabilizer. NACA 4415 has lower vibration compared to NACA 0021. Second, higher forward speed gives higher power acceleration amplitude. Third, power acceleration amplitude decrease with the increment of rotor rotational speed. This condition is so-called blade passage frequency. Fourth, pylon firing reduce the acceleration on the vertical tail. Ellipsoidal pylon reduce acceleration better than rectangular pylon. Fifth, NACA 0021 fluctuate with higher displacement compared to NACA 4415. Higher speed give higher vibration. Pylon reduce vibration by lowering the displacement. Ellipsoidal pylon reduce more vibration compared to rectangular pylon. So, based on this result, I managed to identify the frequency rotor hub wake that occur at 1 omega. Next, pylon configuration can reduce the wake. This result is agreeable with other researchers since they found out the same thing. In conclusion, the objective and scope of this project are successfully achieved. In this experimental work, the two types of airfoil, which are symmetrical and cambered, were experimented in various helicopter advance ratio to quantify the frequency and horizontal displacement of vertical tail due to unsteady helicopter rotor hub wake. Subsequently, the findings of this research work have potential to minimize this long-running tail shake problem that undoubtedly could benefit to entire growing helicopter industry. Improvement and future study. Firing can reduce wake, which means the helicopter stability can be improved. Design of vertical stabilizer also give an impact to the vibration. Horizontal stabilizer and tail rotor must be considered in order to apply this result to actual helicopter. The position of horizontal stabilizer may give contribution toward the vibration. Tail rotor of helicopter mainly used to counter induced moment from the main rotor. The most important thing, the structure may lead to damage when the specific frequency from the wake is combined to the main rotor and also tail rotor frequency. The helicopter may become failure and crash. For future study, the study must improve the behavior effect from the horizontal stabilizer and also tail rotor. Before I end this presentation, I would love to highlight the difficulties that I faced throughout this project. First, going through the process of designing and installing the tail are quite tough since I have to study about the parameter of the tail boom, brainstorming on how to fabricate the tail boom and install it properly into the generic model. Second, in order to perform PSD and displacement analysis, I need to explore more about LabVIEW and how to create a program. Third, my analytical skills are being challenged when I have a lot of data from the experiment with different configurations. I have to study the data one by one in order to get the outcome. Lastly, due to the COVID-19 pandemic, everything has changed, including presenting this project. So, I get a lot of new skill while preparing this video, which could be used in the future. Thanks to everyone. I'm sure all these things could help me improve myself in the future. That's all from me. Thank you very much for watching this video.